Today we are walking through a Python implementation of experiment 3 which focus on the Nyquist-Shannon Sampling Theorem, Aliasing and signal reconstruction. So before we jump into the code, let's quickly review our theoretical baseline. Our signal consists of two tones, a 5 Hz tones and a 12 Hz tones. This means our maximum frequency is 12 Hz, making our theoretical Nyquist rate exactly 24 Hz. As calculated in our mandatory validation step, if we undersample this signal at 15 Hz, we expect the 12 Hz tone to fold or alias down to a 3 Hz tone. Let's run the code and see this in action. So looking for it, initialization block, we can see a setup of FS cases to test our three critical scenarios. Above Nyquist, that is 15 Hz, at Nyquist, that is 24 Hz. That is exactly of 2 of maximum frequency. And the below Nyquist, our undersampled case at 15 Hz. Next, we defined our core function, the original signal. Function mathematically generates our two tones waveform and the sinc interpolation. This function performs the actual reconstruction. It takes our discrete sample points and build continuous time waveforms by superimposing sinc function. And the finally get magnitude spectrum. This function uses the fast Fourier transform so we can analyze the frequency component of our signal. We run the simulation loop which iterates through our three sampling cases. Look at first result. So we can see here in the top of this result, the red stream represents our discrete sample taken from the continuous gray frequency line. Because 50 Hz is well over our 24 Hz Nyquist requirement. We have plenty of data points here, you can see. And in the middle, the blue dashes line in our sinc reconstruction signal. As we can see, it perfectly traces the original signal. And the bottom left frequency spectrum, the math matches the reality. We clearly see two priest line peak exactly. That's 1 and 2 peak, where we expect them at 5 Hz and 12 Hz. The reconstruction error on the here you can see the reconstruction error and the bottom right is practically 0. Moving down at the Nyquist case of 24 Hz, we are sampling right on the theoretical edges, while the frequency spectrum still correctly identifies the 5 Hz and 12 Hz peak. You might notice the time domain reconstruction in the middle plot is slightly aligned compared to the oversampled case. This illustrates how sampling exactly at the boundary can be highly sensitive to phase shift in practical application. And finally, we reach most critical part of the experiment, the below Nyquist case at 15 Hz. Here we are intentionally violating the sampling theorem. Here, take a look in the middle plot. The blue reconstruct waveform looks completely different from the gray reference signal. The information has been corrupted. The true diagnostic in the magnitude spectrum. Here, true diagnostic of the magnitude spectrum. The peak at 5 Hz remains intact because it is safely below our folding frequency of 7.5 Hz. However, the original 12 Hz peaks has completely disappeared. In its place, exactly as we predict in our manual calculation, a false Alice peak has appeared at 3 Hz. You can see here. This provide a perfect visualization confirmation of Aliasing. Higher frequency marks in themselves as lower frequency due to an insufficient sampling rate. So to wrap up this simulation successfully verifies the sampling theorem. It demonstrates that to faithfully reconstruction a signal, we must sample at a rate greater than twice the maximum frequency. Failure to do so result in unrecoverable aliasing as we clearly visualized with our undersampled 3 Hz ghost signal. Thank you for watching this video.